see and get to know a bit about the elements. A visual exploration of every known atom in the universe. And let's start with the front page. C stands for carbon. N stands for nitrogen. O stands for oxygen. S I C for silicon. B for phosphorus. S for sulfur. Cl for chlorine. R for argon. Ge for germanium. Sn for tin. Sp for antimony. De tellurium. I for iodine. Xe xenon. Po for polonium. Ad astatine. Rn for radon. Let's begin. There is not anything which returns to nothing, but all things return dissolved into their elements. Lucretius Terrerum Natura 50 BC. The periodic table is the universal catalog of everything you can drop on your foot. There are some things such as light, love, logic, and time that are not in the periodic table, but you can't drop any of those things on your foot. The earth, this book, your foot, everything tangible is made of elements. Your foot is made mostly of oxygen, with quite a bit of carbon joining it, giving structure to the organic molecules that define you as an example of carbon-based life. And if you're not a carbon-based life form, welcome to our planet. If you have a foot, please don't drop this book on it. Oxygen is a clear, colorless gas, yet it makes up 3/5 of the weight of your body. How can that be? Elements have two phases, their pure state and the range of chemical compounds they form when they combine with other elements. Oxygen in pure form is indeed a gas, but when it reacts with silicon, they become together the strong silicate minerals that compose the majority of the Earth's crust. When oxygen combines reactions with hydrogen and carbon, the result can be anything from water to carbon monoxide to sugar. Oxygen atoms are still present in these compounds, no matter how unlike pure oxygen the substances may appear. And the oxygen atoms can always be extracted back out and returned to pure gaseous form. But short of nuclear disintegration, each oxygen atom can never itself be broken down or taken apart into something simpler. This property of indivisibility is what makes an element an element. In this book, I tried to show you both faces of every element. First, you will see a great big photograph of the pure element whenever that is physically possible. On the facing page, you will see examples of the ways the element lives in the world, compounds and applications that are especially characteristic of it. Before we can get to the individual elements, it's worth looking at the periodic table as a whole to see how it is put together. Here it explains it all. The first elements, then the width central, then the lower left triangle. It gives you the seventh groups, explains it all. And the first one we have is hydrogen. Look at that. Look how beautiful. So the stars shine because they are transmuting vast amounts of hydrogen into helium. Our sun alone consumes 600 million tons of hydrogen per second, converting it into 596 million tons of helium. Think about it, 600 million tons per second, even at night. And where does the other 4 million tons per second go? It's converted into energy according to Einstein's famous formula. About 3.5 pounds per second's worth finds its way to the earth, where it forms the light of the dawn rising, the warmth of a summer afternoon, and the red glow of a dying day. See? The hydrogen is the lightest of all the gases, lighter even than helium, and much cheaper, which accounts for its ill-advised use in early airships, such as the Hindenburg. You may have heard how well that went, though, in fairness, the people died because they fell, not because they were burned by the hydrogen, which in some ways is less dangerous to have in a vehicle than, say, gasoline. Hydrogen is the most abundant element, the lightest, and the most beloved by physicists because with only one proton and one electron, their lovely quantum mechanical formulas actually work exactly on it. Once you get to the helium with 2 protons and 2 electrons, the physicists pretty much throw up their hands and let the chemists have it. And then it gives you the element is the atom's weight, density, atomic radius, everything. And here you have helium. We all know this. You have a party with balloons, you have this. Or in the store, when you want a big balloon and be floating in the air, you want this, right? Helium is named for the Greek god of the sun, Helios, because the first hints of its existence were dark lines in the spectrum of sunlight that could not be explained by the presence of any elements known at that time. It might seem a paradox that an element common enough to fill party balloons with was the first element to be discovered in space. The reason is that helium is one of the noble gases, so named because they do not interact with the common riffraff of elements, remaining inert aloof to nearly all chemical bonding. Because it does not interact, helium could not easily be detected by conventional wet chemical methods. As a replacement for hydrogen in airships, helium, which is completely non-flammable, has much to recommend. The main problem is that it's a lot more expensive and provides somewhat less lift. Anyone want to go for a ride in the low-bid model? The helium we use today is extracted from natural gas as it comes out of the ground, but unlike all other stable elements, it was not deposited there when the earth was formed. Instead, it was created over time by the radioactive decay of uranium and thorium. These elements decay by alpha particle emission, and alpha particle is simply the physicist's name for the nucleus of a helium atom. So when you fill a party balloon, you're filling it with atoms that just a few tens of hundreds of millions of years ago were random protons and neutrons in the nuclei of large radioactive atoms. That frankly is weird, though not as weird as the way lithium messes with your mind.